Thanks everybody for attending. I'm a guest host for the seminar. I'm Chris Snyder from M-Cubed. It's a joint EOL M-Cubed seminar today. Our speaker I'm pleased to introduce is Ollie from, didn't prepare my, okay. So Ollie's a recent postdoc, came to NCAR from the University of Exeter. He did both a bachelor's and a PhD there. He comes from a long line of physicists like Joel Charney, who've come to our field to help us out. So today he's going to talk to us about work that is related to his thesis work, about using refractivity signals from aircraft to estimate water vapor. Thanks.
Thanks for the introduction. Yeah, really fantastic to be here and sort of share some of the work I did during my PhD. So this is measuring humidity. It's plain and simple. It's not as hard as you think. So a little bit about me. So yeah, I did my postgrad and bachelor's at actually in the astrophysics department at the University of Exeter. So a little bit of a strange background, I suppose, but I was funded by the UK Met Office for this project, as well as the Harry Otten Foundation. So a bit about me. I love coffee, absolutely love running as well. And my favorite thing of all is weather. And what better place to do weather science in Colorado? So this was where I did my PhD. This is the physics building at the University of Exeter. Ugly grey block, and we were kind of in the middle of it. See if I can use this now. Oops. I was in the middle of the building, just about here. So other things about Exeter. So this was the world famous Square Pizza, supposedly the waterfront restaurant, one of my favorite places to go. It was a great bar as well, really pretty along the riverfront. This is where I used to live, at the quayside at the University at Exeter. It's a very nice place to live, do my PhD. Greenbow Running Club, a lot of great memories here and a lot of great people. So let's get on to the interesting stuff. So problem statement, measuring humidity is currently very difficult to do. So bespoke instruments are expensive. If you're designing a new instrument, it takes a huge amount of money to do so, and they lack the ability to adequately capture the full temporal and spatial variability of humidity in the lower atmosphere. And this is a problem. As the resolution of forecasting models increases, we really need to be able to capture the true variability of humidity in the lower atmosphere. And in fact, the World Meteorological Organization, this observation system capability analysis review, their goal requirement is actually measuring specific humidity to an accuracy of about 2 grams per kilogram, and actually a 5 minutes timeliness. So it's incredibly rapid observations. So rather than starting from trying to design a bespoke instrument, is there things around us that can kind of tell us some information about the atmosphere? Is there stuff that is giving us useful information that we just need to tap into? So this is where the idea of opportunistic observations come in. So this is kind of a slide that summarizes basically my whole PhD. This is the whole thing I was working on. And the basic idea is that commercial aircraft transmit radio signals for air traffic control purposes. So they transmit this thing called the automatic dependent surveillance broadcast. It's automatic because there's no pilot input. The aircraft will just transmit this twice per second. And it's dependent because it contains information about the aircraft's state vector, things like position, speed, heading. And it's a surveillance broadcast. It's for air traffic control. So these signals don't travel in a straight line through the atmosphere. So the atmosphere has a refractive index, and anything with a varying refractive index will cause light to bend. So these radio signals, they actually follow a curved path through the atmosphere, much like in this figure. So this has the strange effect of making aircraft appear higher in the sky than they actually are. So where the aircraft reports itself to be is here, but we see it up here. So there's kind of this shift in apparent position of the aircraft. And this is the key thing that contains the atmospheric information. So this difference in the apparent and observed, true position contains information about the refractive index structure of the atmosphere. So to do this, we use something called an interferometer, which I'll describe the principles behind in a little bit. And the invention, sort of originally designed in 2019, and I've just been working on it since, starting at NCAR. So the idea of using aircraft radio transmissions for atmospheric information is not without precedence. So already Meteorological services like the UK Met Office and the Dutch Meteorological Office, they use MODES, so this mode-selective radio transmission for wind data, and extremely high density wind data over Europe. So MODES is this kind of burst transmission, or squitter as it's called, and contains information about the aircraft position, heading, speed, things like that. So what I'm using is ADS-B, which uses the same kind of signal structure as MODES, and it's actually encoded using something called pulse position modulation. Now, the structure of this signal will be important for later, but essentially how it works is for every half microsecond, the signal is on and then it's off, that encodes a 1, and then vice versa for encoding a 0. It's off for the first half microsecond and then on again. And this repeated sort of flashing encodes information about the aircraft position and a variety of other information. So already it's been sort of explored to use this data to get sort of mean layer air temperatures using ADS-B reports. We've tried to develop an extension to the existing MODES network to basically get refractivity information. So kind of a little crash course on refractive index. You've probably, this is high school stuff, but the air does have a refractive index. It's extremely close to 1. But the similar effect happens as in this pool. So you've got a very large refractive index gradient here. It goes from essentially unity to 1.3. And as the light passes through this interface, it refracts and undergoes this bending. So where you see the man's head, this is looking through the air. It's a relatively constant refractive index. The light travels in a straight line. But where it passes through an interface, it shifts the apparent position of the object. So this effect is a really extreme example. This is occurring over meters. But in the atmosphere, the same effect will occur, but over hundreds of kilometers. So this is already used by, for example, GNSS radio occultation. So you have a GPS satellite transmitting radio signals, and these are received by a low Earth orbit satellite. And as the low Earth orbiter is occulted by the Earth's atmosphere, the signal passes through the atmosphere and undergoes bending. And using some clever inversion techniques, you can turn this bending angle into a profile of refractive index. So we tend to not use the refractive index. We tend to use something called refractivity, which is just the excess above unity of the refractive index. So this 330 part will be the refractivity. So this depends on the hydrostatic atmospheric density. This doesn't vary massively over the course of hours. It's this water vapor that varies massively, over very short time scales. And this is the key bit they're interested in. So when I say measuring humidity, what we're actually measuring is refractivity, but it's modulated by humidity. So any variation in refractivity will be dominated by changes in water vapor. And so you can get this humidity data out. So the instrument itself, so this is a little interferometry crash course. So I'm from an astrophysics department, and interferometry is used to image these extremely distant celestial bodies. They're incredibly small in the night sky. But with this technique, you have sort of unprecedented resolving power. So the idea is that you have 2 or more receiving elements. The signal is received at for example, in this case, the upper element before it's received at the lower one. And this induces a phase difference. So if you try to sort of time the difference, it would be on the order of picoseconds. You just can't time it, it's just too fast. But the phase difference is measurable. So the signal received at the lower antenna will be in a different phase if you think of like an electromagnetic wave. It'll be in a different phase when it reaches the lower antenna. So if you know the phase difference, you can back out this angle of arrival. So that's basically the whole principle of this instrument. We can basically get angles of arrival just by looking at the phase difference across these elements. And another key bit of information we have is the position of the aircraft. This is inside the signal. So we know where the signal came from, and we know the apparent direction it arrived at. That gives us information about how that signal has been refracted through the atmosphere. So you can go truly insane with this kind of technique. So, for example, with our 13.9 meter baseline on the radar tower, we can resolve, in theory, about 4,000th of a degree. You can go absolutely insane with this. So, for example, the Event Horizon Telescope, by combining multiple telescopes, effectively had a baseline the size of the Earth. And with this baseline, you can resolve 5 billionths of a degree angle difference. This is like resolving an apple on the surface of the moon from the Earth. So it's just unprecedented resolving power. And in fact, it enabled us to take the first image of a black hole. So this is M87 star. And what you're looking at here is this black circle in the middle. This is basically the event horizon, so no light can escape. The gravity is just too strong. And this ring around here is the accretion disk. So material that's been superheated and has started glowing just because of the intense gravity. It's traveling millions of miles per hour. So, and this is 55 million light years away, and we were able to image it. So it just shows the power, the resolving power of this technique. So we have a far smaller baseline, so our resolving power is way lower. But in principle, through sensitivity tests, if we can get to 1/100th of a degree accuracy, we should be able to resolve, useful meteorological variation in the refractive index. So here's basically, the first experiments we did were from the physics building at the University of Exeter. So we have one antenna on the roof, well, not quite on the roof, on the upper floor, and then we have another antenna sort of in the astrophysics department, which is sort of midway up the building. And this picture is kind of a view out from the interferometer. So there's kind of two interesting regions that we saw. So Exeter Airport is over to the left. We could see aircraft, coming into land, depending on the wind direction. But a really interesting area was actually over the channel. So Guernsey and Jersey are down here, the Channel Islands. And depending on the refractive conditions, we could actually see these aircraft coming into land, almost touching the surface, just because the refraction was so strong that the signal was bent over the curvature of the Earth. So this is well below the geometric horizon, but because of refraction, we can still see it. So this is some of the instrumentation work I was doing. So this is a very sort of, early sort of initial test. This was using a horizontal baseline rather than a vertical baseline. But the instrument itself is actually incredibly simple. So you have these two receiving elements, and they're separated by a baseline. This enables you to measure this phase difference based on the angle. And these are connected using equal length monopole cables to something called a software-defined radio. So this is just like a normal radio, but the analog components have been replaced with software, which means you have a lot more flexibility in how you can process this data. So to actually get this angle of arrival data out and the aircraft positional information, you take the conjugate product of the voltages received from both antennas. And what you get is this amplitude term, this V squared. This is the pulse position modulation, which actually contains information about the aircraft location. But you also get this phase term. And this phase term enables you to back out the angle of arrival. So you've kind of killed two birds with one stone here. You've got the amplitude information and the phase information, just from these three bits of equipment. And I think the simplicity is like why we're so excited about this. I mean, this is very sort of DIY kind of science, so the results are a little bit rubbish at this stage. But I think we're making good progress in terms of cleaning this stuff up. So the next stage was actually doing a proper observation campaign. So what we did was use the Clee Hill Weather Radar Tower. This is partly Met Office owned, and this is in Shropshire. And you can just see how bleak it is. I mean, it's on top of a hill in the middle of nowhere. But it's the perfect place to see a huge number of aircraft. So what we used was, instead of these cheap radio antennas, we used Yagi-Uda antennas. So these are basically TV aerials, and they act as the interferometer elements. This is some observational data. So what you're looking at here is, on the vertical axis, is the observed angle of arrival. So this is the angle that our interferometer gives us. So I've got a little figure in the top right kind of demonstrating the difference between the two. So we have this observed angle of arrival, and then on the horizontal, we have this kind of reported angle of arrival. So if no refraction occurred, this is the angle of arrival you'd expect. And the difference between these gives you some information on how strong the refraction is. So for high elevation angles, because the signal's coming in at quite a steep angle, the refraction is quite weak. And so the reported and observed are very close together. But something interesting happens when the aircraft elevation drops. The observed angle of arrival tends to level off, whilst the reported angle of arrival keeps dropping. And this is kind of, if you imagine the sun sort of setting, it's almost like it would just stop, but the actual true position of the sun keeps dropping. So you can still see it above the geometric horizon. So we have this separation of these two angles, and this contains all the atmospheric information. But not just atmospheric information. You can see it's very noisy, and this has been an absolute nightmare to deal with, and I'll talk a little bit about it, well, just now actually. So the principal source of uncertainty, we think, is something called multipath. So what we want is the direct signal, the thing that's actually been in the atmosphere and refracted and contains just atmospheric information. What we actually receive is the signal bouncing off things in the foreground. And when this signal bounces off, it's received at the same antennas as the direct signal, and they mutually interfere, which completely corrupts the phase measurement. So we want to be sensitive to this direct signal whilst ignoring the reflected signals. So what you're looking at here in the bottom left is one of the earliest ideas was to basically just put a big screen on one of the lower antennas to just block it. This did not work. I'm not going to go into the detail. It was an absolute nightmare, but we came up with a sort of a better way to do this. So actually exploiting the radiation pattern of these antennas. So Yagi-Uda antennas, they consist of these, you can see these like vertical lines on this main post here. So these vertical bits here. So we have a single driven element. So if you're transmitting a signal with this, this would be the bit that's connected to, you know, a circuit. And then these parasitic elements, they interact with this electric field, emit their own electric field, and by spacing them carefully, you can actually cause them to constructively interfere when they re-emit this signal. So this GIF kind of shows how this works. So they're each absorbing and then re-emitting the signal, and you can see they constructively interfere in one direction, destructively interfere in the opposite direction. Now this is a key thing because it means the antenna itself is sensitive to certain directions rather than others. So we have this main lobe where it has very high gain, signals received here, received very strongly. And then you have these nulls where signals received here, they're very weak, or you don't receive them at all. So can we use this to kind of be more sensitive to the signal we're interested in rather than the reflected signals? And the answer is yes, you can do that. So this is an example of an experiment we did by basically just tilting these antennas to place the first null where we think the reflections are happening. So this top plot is basically a view of the sky. You can imagine this little window into the sky. And these lines are flight paths. So literally just planes, well, observed flight paths. So they basically imagine just planes flying across the sky as if you're just looking at them. Except there's something weird going on here. There's these ripples going on. Now the aircraft aren't actually doing that because it would be an incredibly miserable experience to be on an aircraft doing something like this. But what's actually going on here is that we have this sloping hill in the foreground. And when you're looking in certain directions, the direct signal is being received either in phase with the reflected signal or out of phase. And so it's destructively or constructively interfering. When we tilt the antennas up and we become less sensitive to these foreground reflections, something interesting happens. All the ripples tend to just disappear, or they're significantly dampened. And this is because we're just not sensitive to these reflected signals anymore. We're only seeing the direct signal, the thing that actually contains atmospheric information, rather than the reflected signal. And this was a huge suppression from the get-go. So this is an observation minus model, and you can see an enormous spread here where basically these ripples result in this big spread in the observed angle of arrival. When we tilt up, we get a factor of 4 suppression. So we need 0.01 degrees. We got to about 0.03. Painfully close, but not quite there, because they're still contaminated, not so visibly, but you can still see some ripples. So there's some areas we're still not accounting for. So kind of just to summarize this is kind of what's going on. So pointing the antennas directly forward, you have some sensitivity to these reflector signals coming from the ground. Tilting them up, placing it in the null, you lose that sensitivity. So you can really clean up the data. This is a very crude way of doing it. Like this is still quite a broad beam pattern. So you're still, sensitive to some foreground stuff, but also crucially, you're reducing your gain on the horizon. So you're reducing the sensitivity to signals received close to the horizon, where the strongest refraction takes place and that we're most interested in. Can we do better? Yes, we can. So later on, we had another observation campaign, and we ended up with this Doctor Who looking thing, where basically, rather than having a single TV aerial, we had 4 of them. And just like with the sort of radiation pattern before, these interfere, their radiation patterns interfere. So you get a very high gain close to the horizon, but also incredibly deep nulls elsewhere, which means you're even less sensitive to these foreground reflections. So this is, I don't know if you can see that very well, but it's kind of built out of scaffolding pole. So the whole thing's very cheap. I mean, these are TV aerials, they're not too expensive. Scaffolding pole, surprisingly expensive, but also relatively not that expensive. And it's just all kind of built by hand, which was part of the fun of this project, was actually just building this stuff and just trying out in the field. So the results we got from this are actually quite interesting. So this was looking south over the English Channel, and you can see the channel islands here. And these are flight paths. So they're color-coded by this refracted angle, this difference between the observed and reported. And you can see the more distance, I guess, the stronger the refraction. But also there's like low elevation, or low altitude aircraft here, where the refraction is stronger. And then we've got Bristol Airport up here. So we had some really strange results from this. So this right-hand plot is the observed angle of arrival, so the elevation, versus the observed minus model. So we had a reference model using the UKV model, and basically any change compared to this model, we can plot sort of a temporal change. So what's happening here, above this elevation, the refraction is weakening with time. So the observed refraction is growing weaker compared to the reference model. But the opposite happens at lower elevations, where we actually see a strengthening in refraction. So you get this really strange helical structure. And honestly, it was very difficult to work out what was going on. We're sort of very sensitive to slight changes in atmospheric conditions. But there was some kind of strengthening in refraction at lower elevations and a weakening at higher elevations. I think in future it'd be good to compare this to some reanalysis data from that time. But I think we're resolving structures smaller than what the model can represent potentially. But that's something to worry about in the future, I think. So we also saw some really interesting stuff with training exercises. So we saw one aircraft just doing the loops, going down to land and then coming up again, and just repeating this very repeatable flight path. So you'd expect with the observed refraction it would be relatively constant. But we didn't see that. What we see instead is that earlier times it appears higher in the sky, and then at later times it just appears to drop in the sky, even though the reported altitude is not changing. And then plotting this against a model, you can see there's a systematic shift in the observed position of the aircraft with time. That wasn't due to the aircraft changing position. It must be due to sort of atmospheric changes, weakening the refraction that we see. We also saw some other interesting stuff with this RAF aircraft looping round. So this was at a constant altitude, but because it was so distant, you're kind of looking underneath the aircraft. So this constant circle looks like an ellipse. And you can see sort of very nicely where this is where it says it is in the sky from these ADS-B signals, and this is where we see it in the sky. So much noisier, there's an atmospheric signal in there, multipath signal, there's a whole host of observation errors and useful information in there that's just very difficult to disentangle at the moment. So we have all these angles and this, refraction information, but what can we actually do with this? How can we turn this into humidity data? So one of the things I worked on was actually retrieving initially vertical profiles of refractivity based on the observational data. So I have a ray tracing operator that I linearized and then took the transpose of, so basically taking the adjoint of this, and I use this adjoint to minimize some cost function that I constructed. So for a single ray, the cost function will be something like this. So we have this observed angle of arrival that I trace out in this time-reversed frame, and I trace it out to the reported distance of the aircraft. Now, because I don't know the true state of the atmosphere, it'll land at some different point than where the aircraft reports itself to be. So my goal was to minimize this difference, keeping this angle constant and this distance constant by only changing the refractive profile of the atmosphere. So for a single observation, this is an ill-posed problem. The ray has an infinite number of paths between here and the aircraft location. It could go, something crazy up here, all around, and then land at the aircraft. Obviously, it wouldn't do that, but for a single ray, it's not a well-posed problem. If you have multiple aircraft at different locations and heights and distances, it suddenly restricts the number of solutions you can get. And so with multiple aircraft, it becomes like a tomographic problem, and we can reconstruct the most likely atmospheric profile that explains the observed refraction. So we can also use this adjoint to work out the sensitivity of this cost function with respect to the refractive index at different altitudes. So you can see there's enormous sensitivity near the surface where the gradient is very large, where changes in refractivity near the surface have massive downstream effects. So it's very sensitive to an accurate measurement at the receiver as well. And then it sort of drops off with height eventually. So these are some initial refractivity retrievals. So this is from a preprint that was just yesterday accepted for publication, which is great news. But this was using observational data to retrieve refractivity profiles. So we start off with some first guess that we think is relatively close. And then we sort of run this minimization. So we minimize the difference between the modeled height of the aircraft and the reported height of the aircraft. And by doing this optimization procedure, we get a retrieved profile. So you can see there's relatively good agreement with the radiosonde value, this sort of dashed line here. But at higher altitudes, it gets very noisy. And this is partly because of multipath. We're not just seeing an atmospheric signal. We're seeing very complicated observation noise. And at this point, I wasn't able to quantify the observation error statistics, It's a really complex mix of atmospheric multipath, which I'll talk about in a little bit, these foreground reflections, but then also just the instrument itself. We build it from scaffolding pole. It's not going to be, the most precise thing ever. So to kind of, show what this optimization algorithm is doing a bit clearer. So on this left-hand plot is basically kind of a view of the flight paths, the reported flight paths in the sky. So these black points are where the aircraft says it is in the sky. We start off with this first guess refractivity profile, and the rays land here. So, they're not being refracted as strongly as the true aircraft. When we run this optimization procedure, we're basically moving the endpoint of the ray closer to the true reported altitude of the aircraft, so they get moved down this green line. You can't fit these all simultaneously because the atmosphere isn't 1D. We have observation noise, a whole host of regions. But it's kind of doing generally the right thing, moving the mean of this difference towards 0. So this was, some early refractivity retrievals we did. We can also look at time series observations. So this was from September last year, and this was overnight. And what this is an observed minus model refracted angle. So comparing the observed refraction to one modeled using radiosonde data. And our reference was from 11 o'clock UTC. So you can see this split in color is due to distant dependent refraction. So the color scheme is with distance. And when there's a separation, the refraction depends on distance. When they come closer, you kind of lose that. But with this spike here, this was during a rain shower, and this was a local change in refractivity, quite an enormous change from a dramatic rise in humidity. All the aircraft appear higher in the sky because of that. And then it sort of drops back as the rain shower passes over. So there's a huge amount of really complicated information here where we have distant dependent variation in refractivity, but also very local changes. And they have sort of very different effect on the observations. So talking a little bit about modeling some of this observation noise. So on the left-hand side, this is a LiDAR data sort of plot of Clee Hill. So this is the hill here, there's a little valley here, and this little star here is our interferometer. And these black points are where I modeled reflection points to be. And I use this to kind of inform where the nulls of the antenna should be placed. So we want it primarily here. But there's reflection points all over the place. It's almost impossible to block them out simultaneously. So this right-hand plot is a result from that modeling. And basically what you're looking at here is a view of the sky. And if you have a signal received here, how much is the phase shifted by the reflected signal? So this phase pattern, it sort of wraps around between 0 and 2 pi. But you can see it's kind of tilted like this. And this is because the slope of the hill was tilted like that as well. So we kind of have this tilted multipath environment, which makes modeling this actually quite difficult. It's very sort of distant dependent, foreground dependent. And this lower plot kind of shows the impact. So this is observational data, and you can see the ripples. So the ripples correspond to where there's sort of phase perturbations here. Results in this rippling pattern. So it's not just foreground reflections that interfere with the direct signal. We can actually receive the same signal from multiple different directions within the atmosphere itself. So the path of the light in an atmosphere will be governed by Fermat's principle, the path of least time. But there could be multiple paths in the same atmosphere that have the same minimum time. So for example, here the rays are clustered. All the rays coming from here have exactly the same travel time. And so we're kind of receiving, if we have two aircraft in these regions, we can kind of receive the signals from them simultaneously. This is very challenging to deal with. This will take a lot of more wave optics approach to sort of deal with in the future. But it also results in an increase in radio power in these areas. So where the rays are concentrated, you have way more signal being concentrated there. So one thing we actually saw in the observational data was sometimes an aircraft will be traveling along and it'll be sort of very dim, and then it'll suddenly dramatically increase in brightness as it goes in these atmospheric waveguides, these ducts. And that's just basically all the signal just being concentrated within this small region. So a little bit more on the foreground reflections. So this was some stuff we did back at the physics tower. So there's like multiple different areas reflections can come from. And one of them is the Great Hall, which was sort of in the center of campus, interfering with the direct signal from, just passing through the atmosphere. And this was interesting because it results in this kind of observed minus reported, so this refracted angle profile. So this is looking sort of along azimuth, And if there wasn't any noise, you'd expect it to be kind of a straight line with only an atmospheric signal. But what we see is these random jumps, these big random jumps. But they're not truly random because there's actually two aircraft here in the same flight corridor. So these blue and red points, they're different aircraft, but just happen to be in the same region of the sky. And they follow exactly the same pattern. And this is entirely a foreground reflection thing. When you have a static foreground, they're going to produce the same multipath environment. So perhaps, it might be possible to get an extremely complicated map of the foreground specific to an instrument and just correct this out potentially. There's one more way we can also deal with this. So the key thing is the direct signal is the least time signal. Based on Fermat's principle, this signal will always be received first before any reflector signal will be. If you sample fast enough, could we get the phase measurement just from this direct signal before the reflector signal has had time to interfere with them? And potentially you can do. So we were doing a 10 megahertz sampling. So we can sort of reduce the amplitude of these foreground reflections if the extra length due to reflection is less than 30 meters. So yeah, 1/10 of a microsecond. So what you're looking at here is an actual ADS-B pulse that we saw. So you can see how the signal ramps up and then drops off, sort of encoding the 1 and 0s. At the front of the pulse of each of these individual pulses, the phase variation is much lower than at the back of the pulse, where the reflector signal has started to interfere with the direct signal. So if we can get our phase measurements just from the front of these signals, we should be able to, remove this extra reflection component. So let's see what happened. So this was a view of the sky. This is elevation versus azimuth. So you can see these flight paths in the sky. This was before using the leading edge method. This was just using the entire pulse with the reflected signal. But when we sample extremely quickly, we see those phase variations disappear. The ripples kind of just disappear. We're seeing the direct atmospheric signal here. Still a little bit of noise, but we've significantly reduced the impact of that multipath. So there's multiple ways we could deal with this, and we haven't fully decided which one's the best way to go. So we have this beam forming, just be less sensitive to the reflections. And then we also have this leading edge method where you just sample so quickly that the reflections don't matter anymore. So bringing it back to, how can we actually use this data, sort of in an MWP model perhaps. So there's analogies with radial occultation here, where we have this bending angle. The signal is sort of bent by the atmosphere, except in our case, both the receiver and the aircraft are embedded entirely within the atmosphere. But we also have a huge number of aircraft, over like North America and Europe. So you can get a huge number of bending angle measurements from different regions of the atmosphere in a very small amount of time. And these aircraft are constantly transmitting, as they're coming into land. So there's a potential to sort of use this observational data, using existing tools like the ROPP. So the radio occultation processing package, we adapted this basically to assimilate some of this bending angle information. So the benefit of doing this is that the uncertainty in the bending angle is linear in the angle of arrival. But we don't actually know the bending angle directly from the get-go. So the bending angle depends on these 4 angles. So the angle of arrival, this angle subtended at the center of the Earth, and also this emission angle. But we don't know the direction of the signal when it leaves the aircraft. And this depends partly on the atmospheric state here. So it depends on some model state as well. So we can't actually directly work this out from the get-go. But what we do know from the get-go is this angle here. This just comes from the position of the receiver and the position of the aircraft. So we have an observable quantity, and we have a quantity that we can model using an atmospheric state. So we have a forward operator here. Could we use this forward operator to assimilate these observations? I never actually got to that point. So, this will be a sort of a topic of future work for, whoever comes after me, I suppose, in the PhD project. So just one more thing I want to say, why we're excited about this technique is that it really does complement radio occultation. So the uncertainties in radio occultation, increase quite a lot, very close to the surface. But that is where pretty much aircraft, spend most of their time. The signal is always going to be, within the lower atmosphere from the receiver to the aircraft. So it could really complement radio occultation within this key region here where the uncertainties grow quite large in radio occultation. So I think I'm a little bit over time, but some concluding thoughts. Opportunistic observations, they're cheap. They're already having an impact on forecasting skill with the Mode S observations. We've demonstrated sensitivity to variations in atmospheric structure and also, changes in humidity. So I didn't get to assimilate this during my PhD project, but I think the next steps will be trying to assimilate some of this observational data, whether it's synthetic, your real observations we have. But also a key thing we need to do is sort of better quantify these observation errors. They're going to be very specific to a particular site, the foreground environment, just a whole host of things going on. And that's pretty much it. So yeah, thanks everyone so much for listening. I hope you enjoyed the talk.
Questions? I'm going to go Dawn first.
Yeah, a couple of questions. One is, what wavelength or frequency are these observations?
This is the 1090 megahertz, so it's about 27 centimeters.
Yeah, okay. So can you give us some feel for like how many airplanes are needed in order to get reasonable results that are useful in terms of weather prediction, et cetera?
So for my sort of direct retrievals, you kind of need a suitable distribution with height, but you get that from an airport. You see aircraft coming down all the way to the surface. For data assimilation, I think each observation is going to tell you something about the atmosphere. And I didn't try an assimilation experiment, so I'm not sure, but I think you could probably get away with fewer aircraft, I guess, if you have some background idea of what the atmosphere is doing. But we were receiving, millions of observations within a few hours. It was just an obscene amount. So most of that you've just got to chuck away.
Okay, one more. Does this operate well over a water surface?
So I'm not sure,
Okay.
but the multipath it'll be sort of very specular at that point. But maybe, with some of the techniques we're developing, it might actually work better because it's less complex, I suppose. Maybe not straight over the ocean, but yeah, I'm not sure.
Yeah, okay.
Fun. You didn't mention it, but in our literature, turbulence acts to change the humidity. And so I'm wondering whether some of the variability you see is just the fact that it goes through the atmospheric boundary layer when we see it, and turbulence changes all that. And so then it's going to be a function of stability, okay, whether it's a daytime measure or nighttime measurement, et cetera, like that.
Mm-hmm. So, so some of our observations, some of the craziest stuff we see is when the actual elevation of the aircraft is negative. So that ray is passing extremely close to the surface. And we see some really wild stuff. So yeah, I think there is a lot of turbulence. For the higher elevation stuff, the ray doesn't spend a huge amount of time within a particular layer of the atmosphere. But yeah, for when you're looking down, like almost in like a radial occultation kind of geometry, there's some crazy stuff going on that we don't understand what's going on.
John Wingard wrote this paper. It's called Refractive Index Turbulence, where he looks at many of these things and the role that turbulence plays in changing that.
Other questions?
Yeah, it's a nice presentation. It's like you measure the in-phase and quadrature signals when you receive it in SDR. Is that right?
What's that, sorry?
In-phase and quadrature signals, I and Q, to get the phase measurement.
To compute the phase measurement?
Yeah.
We do this. We basically sort of conjugate multiply just the two signals, and just the phase of that will be the phase difference.
Okay, it's a complex amplitude and phase signal.
Yeah.
I want to know what kind of decorrelation time those kind of things have it. Because that's related to a lot, say about turbulence and other things related to that. It's,
I'm not sure.
Okay.
Sorry.
okay, thanks.
Can I toss to you?
That was really great and interesting talk. I was wondering, so with the airplanes flying at different heights, you are getting like vertical resolution. And I was curious with airplanes at different distances from your antenna, is your model able to get some like horizontal spatial resolution?
So for the 2D stuff, there's kind of, it becomes, I think for like a direct retrieval from one line of sight, because there's kind of like multiple different atmospheres that could result in the same refraction with distance as well. So part of the reason I chose a 1D one was because it constrains the solutions far more. I think for the 2D stuff, I think you'd need a really good sort of prior atmosphere, like from a background state. So I think that'll be the next steps, actually assimilating the data. You already have a good idea of what the atmosphere is doing, or goodish idea. And I think, that kind of makes the problem, there's like a unique solution then, I think.
Yeah.
But there's definitely, distance dependent stuff going on. Yeah.
Okay, yeah, thanks.
Other questions? Okay. Let's see if we can do this. Come on.
Yeah, I was curious if your group has like brainstormed some kind of like field campaign with a research aircraft that could produce signals that are like targeted specifically for this purpose.
Yeah, so we already worked with in the UK you've got this FAM aircraft, the Facility for Airborne Atmospheric Measurements. So we used that to get ground truth data. It was such an incredibly chaotic day that it was very difficult to interpret the results from that. But yeah, I think if it was transmitting ADS-B and having like a targeted thing like that, I think it'd be really informative, at least for like a single aircraft.
Yeah, cool.
Okay, I have a question. When you showed there was a time trace of, I think it was an O- model, refractivity, and you said there was a thunderstorm and there was a spike in the difference. How much, that variability, how much water vapor, if I map that back to a typical amount, delta in water vapor, how big is that?
Honestly, I'm not sure. So unfortunately we didn't have like a weather station on site. A lot of the observations were done with like a handheld thing. It was incredibly crude. And this was sort of, 1 a.m. So there was nobody up there. We're just running it overnight. But I think, future ones, it'd be really helpful to have like local in situ measurements, just to better understand what's going on and sort of, constrain the retrievals.
Okay, I have one more before you go. So, I mean, you see these planes at high, like these paths are almost continuous in time when you show them the plot. That's really high frequency. But this, the specular stuff coming off the surface, that's varying in time, right? Because it's bouncing. What about just doing temporal averaging on those signals?
So, yeah, I think that's actually the next step. So I think they do it with, it was GNSS, like maybe not reflectometry stuff, it's like polarimetric stuff. And like if you get enough observations, you can sort of really characterize the multipath environment. I think that'd be the next step, is to build a static model of the multipath and then just subtract that out from the observations. I don't think it depends on, if it's like, well, it probably does depend if it's snow covered as well. There's like a whole host of like things going on there. But yeah, I think when it's a static thing like that, it could be subtracted out. We just need more data. And it's very difficult to go out there and run this thing continuously just because of the volume of data.
Okay.
Thanks, nice presentation. Just a comment. Is that function of the frequency you got at 27 centimeter? If it had been much shorter wavelength, would have been much better for your measurement, or?
So, because this is an opportunistic thing, I guess we have to use what we're given in terms of the wavelength. I wasn't sure.
I was wondering, the wavelength has been shorter, would have been much better resolution would have got it. Like maybe 10 centimeters or something like that, into 27 centimeter.
Yeah, I'm not sure how much it would be sort of attenuated by the app. Maybe not 10 centimeters, but I I think the ideal part of this wavelength was that it's not attenuated so much. You just see the refraction.
Okay. Thanks.
Okay, oh, we got one more.
Sorry, sneaking it in the last minute.
So at least reminded me of this. So the water vapor sensing system is a tunable diode laser absorption spectrometer that goes on commercial aircraft. That seems like a nice, yeah, you're aware of it, and so that would be a really nice validation of this effort.
Yeah, so that when I was talking about this, you know, where we don't know the refractivity at the aircraft location, with that you could compute it, and then you could do, you know, the whole bending angle thing, which would be great to do. Another idea we had was for the high altitude aircraft, you know, there's not much water vapor, so you can kind of just assume the refractivity is just hydrostatic, and you have like a reasonable idea of that at high altitude, so maybe use that to get these bending angles. But yeah, there's like, I think that's the nice thing about it. There's so many things to explore here that I just wasn't able to on my own. So I'm hoping to just generate more interest in it and just get more people talking about it, and because I think there's a huge amount that could be explored here.
Okay, let's thank our speaker for a really great talk.
Thank you.